Hello there. My name is Moein Heidari. I'm a PhD student at the University of British Columbia, and I'm going to present our ICCV 2025 paper, SL2A-INR, Single Layer Learnable Activation for Implicit Neural Representation. This work has been done at the University of British Columbia in collaboration with University of Tehran, Ardabil University, and University of Rosenberg. So why do current INRs struggle? Vanilla Relu MLPs underfit high frequencies, which is a problem known as spectral bias. Periodic activations help, but they can be fragile to initialization and hyperparameters. So our contributions are proposing a learnable Chebyshev activation layer that adapts frequency coverage, a fusion MLP where SL2A output modulates each ReLU layer with a skip to carry high frequency signal forwards. And we show strong, robust results across 2D, 3D, and NERF with less tuning. So this slide shows SL2A-INR at a glance. The LA block projects inputs onto a learnable Chebyshev basis from 0 to K, trained end-to-end so that we can control the spectral emphasis. The fusion MLP is a shallow ReLU MLP whose layers are element-wise modulated by the LA block, and a skip helps preserve high-frequency information. And the net effect is sharper reconstruction, faster convergence, and stability across hyperparameters. So as our results, this slide shows our result on 2D image fitting with DIV2K dataset, where we achieve the highest average PSNR and SSIM metrics. Visually, you can see sharper text and edges with fewer artifacts compared to baselines. The takeaway is that the learnable spectral control translates directly into high fidelity reconstruction on natural images. This slide shows our result for 3D occupancy or assigned distance field, where we obtain top IOU across shapes, capturing both smooth surfaces and fine geometries. Moreover, for NERF on Blender dataset scenes with 25 images, we reach competitive to best PSNR, often with fewer views. The results show the approach generalizes across modalities and not just 2D images. Here, we focus on robustness and ablation studies. The learning rate across batch size heat maps show consistently higher PSNR for SL2A over a wide grid. So our method is kind of tuning the frequency friendly. Ablations also indicate that higher K, higher value of Chebyshev polynomials or K, and enabling the skip reliability boost PSNRs. We also examined the NTK eigenvalue spectrum, where we show that slower decay suggests better gradient flow and helps explain stable training as what we observed. Finally, this slide shows the complexity of our model across its ability to generalize. Specifically, SL2A remains computationally efficient across different tasks with a slight trade-off in training time, which is balanced by superior performance in representation quality. Moreover, SL2A distinctly preserves sharp details in super resolution tasks, where you see it proposes less noisy results images, demonstrating its generalizability across different tasks compared to previous state-of-the-art methods. Thank you very much for watching our video. I'm happy to discuss details during the session. You can reach me on Twitter or newly X and find the paper and QR code via these QR code links on these slides. Thank you.